and about nonlinear fluctuating hydrodynamics. Okay.
Thank you. So good morning, everyone. Most people look refreshed. I mean, that's very nice. I mean, a lot of fresh air. So let's see where we stopped yesterday. So I remind you that we had, for these anharmonic chains, sort of written down the full nonlinear Euler equation, and then we simply linearized, and this gave us that very particular, fairly simple system. And I also remind you, so A is the linearized Euler, which depends on the background fields, and I also wrote down the static susceptibility, which is sort of the information. Yes. Yes. Okay, I will. Okay, so that was really much too far. Okay, so I continue in the middle, so I can leave this over there. Okay, and then we had the other quantity, which is the static susceptibility. Now, what we really want to compute is the correlator. I mean, the correlator, time correlator of the conserved fields. And we can compute this already on the level of that very simple approximation. You see, we only have to solve the linearized equation, and remember that we have initial conditions which are random because we want to have this particular static susceptibility. And if we do this, then the result will be that at that level, if I look at now, let's see, what notation did I use here? Yeah. So of course we have done a continuum approximation. So maybe I should sort of say this a little bit. I mean, so here we have the discrete lattice index. So this is the lattice, and then so X will stand for the continuum, and somehow depending on which theory I'm using, I'm sort of switching somewhat loosely back and forth between the two notations. And so here I'm using now. Is that okay, or is it still too far to? Is that still okay? Okay. So I'm sort of switching back between two notations. I mean, so this is the true microscopic 3x3 matrix of time correlations, which depend on T on the lattice index. And in this approximation, which is definitely very crude, so I have to put sort of a real approximately equal. This is simply given by the solution of this equation with this initial condition. And if I solve this, I mean, you see that I get simply minus dxa t. So this is a 3x3 matrix. And in order to satisfy the initial condition, I simply multiply this by c. So on that level, we found this result. And now I told you already yesterday that this A is sort of a nice matrix. It has three eigenvalues, 0, c, and minus c. And so if I sort of plot what I get from this object, and if I take a particular matrix element, so what you will see is that the solution, C is a function of x and t there? C is a function of x and t? No, C is a 3x3 matrix, not depending on x and not depending on t. It's just it's derivative with respect to x operator. Well, I mean, this whole thing, I mean, will be sort of a function of x and t. No? I mean, I take the exponential.
Microscopic ratio.
I mean, okay. So
because A.
No. Okay, so let's first think about. So I mean, you think that's a sufficiently clear symbol or not yet?
Not to me, no.
Okay, all right. So this acting on a function. No, it's just shifting this function by.
Oh, yeah. Once you operate on a function.
Yeah, that's so I'm writing this. So you see, I'm writing kernels of operators, right? I mean, this is.
So S is an operator.
Well, well, okay.
It's a differential operator.
No, dx is a differential operator.
Yeah, but you're setting S equal to something which has a dx in it.
Okay. So S, okay. The exponential of that operator is again an operator which has an integral kernel, and that integral kernel is approximately equal to. No. Okay. Not yet. Okay. All right. So let's try some other notation. Okay. Okay. So I write e to the minus dx of t, and then this has an integral kernel, right? All right. And so basically, I'm identifying. Okay, I understand that it's maybe a sort of a.
Somebody. It's just a correlation function, not an operator.
Yes, but I can also think. Okay, all right. Okay. Well, okay. So it's okay. So what should I do here? Let's see. Let me. Well, okay. I mean, so I'm sort of maybe too loosely identifying things which sort of look obvious to me. I mean, so the point is that I can, if I really put here j minus j prime, I mean, then you can think this as a kernel of an operator, right?
Yeah.
And similar here, I should put here an x minus x prime. I mean, then it's really the proper kernel of the operator as I've written over here.
Okay.
Okay. And so now this kernel is, so to speak, evaluated. Since it sort of depends only on the differences, it's evaluated simply, at its argument, and the other argument is that equal to 0. And of course, the same thing I'm doing over here. I mean, so I do not write it as x minus x prime, but since one argument is kept fixed, okay. Now this becomes sort of, I mean, okay. So it's a slightly shorthand notation. I agree. Okay.
So
yes.
Is the continuous version of S?
Well, no, I mean, it's not the continuous version. I mean, I'm saying that at that level of trying to get to some reasonable description, I have sort of an intermediate approximate result. I mean, that's all what I'm trying to say. And now what does this object look like? Well, it's a matrix, so let's take some matrix element, alpha prime, and then here I take also an alpha prime. And then, of course, since at time t equals 0, okay, so maybe I should have said, actually, this is maybe a little bit confusing here. I mean, what I should have said.
J is X.
What is that?
J is the same as X.
Yeah, that's right. I'm sort of somehow identifying the J and X in sort of, one of them is still sort of a lattice, but already on a large scale, so very fine lattice, and that's identified with the X. Okay, and what this solution looks like, I mean, is that it has simply, because I have 3 eigenvalues, I have simply 3 peaks. I mean, so one to the right, one to the left. So it's a sum of 3. So this as a function of x at time t is a sum of 3 delta peaks. I mean, this is sitting at 0. This is sitting at c times t. So this is my x coordinate. Okay, and here I'm plotting this particular matrix element. Okay. And this other peak is sitting at c minus ct. So all what I'm saying is on the level of the linearized, the approximation which I will find to my correlator simply consists of 3 peaks, one sitting still at the origin, and then there's one peak moving to the right, one peak moving to the left. And then the one moving to, obviously the one moving to the right I will call the sound peak. And the one moving to the left is, of course, the left sound peak. And this one, which is standing still, it's just a traditional name, is called the heat peak. Okay? And so what we have found is and the height of these peaks will depend on, will depend on which particular sort of matrix elements I'm taking. If I take some other matrix element, I will see the same picture, but the heights of the delta, the weights of the delta functions will be simply different, right? That's sort of just a linear structure. And what we have found then is that, at that level of approximation, apparently, there's some mass moving to the right, some mass moving to the left, and something simply sitting still. Okay? Now that, of course, cannot be the full answer.
This is a correlation function?
I'm plotting this solution here as a function of x and t. So I'm saying that initially the C is this C matrix, but the correlator is delta correlated. So it simply starts with all delta functions at the origin. And as you apply this operator, what it happens is that these things are just moving out and one is still standing still because there's one eigenvalue 0. Okay, I have I have eigenvalue minus. Okay, the eigenvalues, maybe I remind you, the eigenvalues of A are simply minus C, 0, and C. Okay? And C has the delta function, they are moving linearly, and that's what I get.
What does the heights represent? The x-coordinates are the eigenvalues.
And this is that function for a fixed choice of alpha and alpha prime as a function of x and t. That's what I'm plotting. At fixed t, I'm plotting this function here. Yeah, and it's just, yeah, okay, that's okay. I thought that was the easy part. Okay.
I missed something in the last lecture, the connection between diffusion and
Okay, that's a good question. Okay, so you see, I mean, I did this very verbally. Now, all what I said is that okay, so maybe I have to remind you. So you see, what I'm doing here is the conserved field times the conserved field with some other. Okay, so I'm computing this truncated correlation, right? And so what I argued is I can do this by solving the macroscopic equation and simply saying that, you know, all what I have to do, because this is a small perturbation, it suffices to solve the macroscopic equation on the linearized level. Okay, so this is what I have done, and what I'm telling you is simply what is the solution of that linearized problem. And what I find is that at that level of approximation, a very simple picture. I have one delta peak to the right, one delta peak to the left, and the other one standing still. That's all what I'm trying to say. Okay? Now it's clear that this cannot be the full physics, right? Because, you know, I mean, there's no reason why this should be sharp delta peaks. So there must be some broadening because of noise in the system, right? I mean, it's clear that this is, I mean, but I emphasize that it's sort of, you know, a very important sort of lowest order approximation. It tells you already, you know, a lot about the system, and of course we will have to refine the pictures as we go on, right? Okay, still lots of problems. Okay.
There is I think it's good if we understand it in the beginning.
Yeah, okay, good.
The equation is deterministic. The equations are deterministic.
Yes.
So you're calculating a correlation function, assuming apparently that the initial condition is noisy. Is it correct?
Yeah, correct. Yeah.
What is this noise?
Okay. What is this noise? So the initial condition is my equilibrium measure, right? I mean, okay. now I have to do the equilibrium. Okay, so this is.
The question is, why don't you include the noise in the right-hand side of your equation? Because this noise in the first.
That's going to come. I mean.
Created the equilibrium.
No. Sorry. No. Okay. So okay. Yeah, that's right. I mean, so here you have these brackets, right? I mean, this is the equilibrium measure, and so maybe I should have said this a little bit more precisely here. I mean, okay, so I don't want to write over here. So the initial conditions. Okay, I mean, I agree. I mean, this maybe was a little brief. The initial conditions are random. The initial conditions for these equations are random. Okay, now what are they exactly? Well, they are a random field which is obtained from this equilibrium measure. Okay. So let's give some name to this. So okay, so that's okay. Yeah, I should have thought about this. Okay. So let's do this more clearly. So I have initial conditions. U vector as a function of x. I mean, I leave out the argument t. I mean, just to indicate that that's the initial condition. Well, this will be white noise. But of course, it's correlated because, you see, I mean, according to that susceptibility matrices, there are, you know, at a given site, there are static correlations. And so the initial measure is u of x prime alpha, u of alpha prime, x prime. I mean, this is just nothing else but a delta of x minus x prime. And so it's Gaussian, and it's delta of alpha minus, and it's C of alpha prime. Okay, sorry, I mean, yeah, and I should have said this better. Okay, so I solve this equation with this initial condition. I compute the correlator, and this is what I find. Okay, and now this wiggle is just more, you know, sort of a claim rather that of course, you know, I believe that should be a lowest order approximation to the function which I really would like to compute. Okay, and so now still questions? Yes. Excuse me, the equilibrium? No, I mean this on the large scale. This is what your equilibrium fluctuations look like.
Equal time.
Equal time. Then this is the time. I put your initial conditions. That's at time t equals 0. That's the field which I have to evolve according to this linearized equation. And then for that evolved field, I compute now the correlator. And the answer will be this formula. And
so that operator acts on u instead of u.
Forget about the operator. I mean, I just sort of look at the final thing. I mean, I mean, yeah. Okay.
So the delta function on the top is some post-grain representation of some short-range coordinates.
The initial measure is it's independent. You know, the equilibrium measure is just independent at every side. So on a large scale, this just looks like white noise.
This particular lattice.
Yeah.
But when you apply this more generally, the delta function means you're looking on long scales compared to.
Or everything. I mean, you know, whenever I talk about the x, I mean, the way you should think about the x is that you know, I'm looking at a very large scale here somewhere my x, and this is sort of many few lattice points. Yeah. I don't, you know, if I add, of course I can add this into my notation because it will become even sort of more confusing, okay? All right, so, okay, so now let's see whether we can, okay, so now the first thing, what you should do is you should add noise to the system, I mean, you know, which should be a sort of better approximation. And so we want to add noise. I had noise in the initial condition, but I didn't have any noise in this equation, right? So add noise. But you know, if you add noise, I mean, that's a general rule. I mean, then we also have to, at the same time, add dissipation. Otherwise, wouldn't be very sensible. So this is sort of Onsager, if you want. So I mean, he understood this point extremely well. And so the way how we do this is that we now write dt of u alpha. So you know, I'm not going to sort of change too much. I mean, now I still want to have the conservation law, of course, so there will be still my A of u. Well, now, if you want to add dissipation, I mean, then this will be sort of a diffusion matrix, which okay, so, you know, I can, okay, which acts on this, and it will be diffusion matrices that are then proportional to the local gradients. Well, and then there will be simply noise. And the way I want to add the noise is that I introduce another matrix B, and then I put this equal to 0. Okay? So now this thing is here white noise. In X and T, so I assume that the currents are somehow essentially uncorrelated. I mean, so you know, it means it's white noise in X and T and independent in alpha. Uncorrelated, independent in alpha, right? I mean, so there's 3 components, and it will be a similar type of relation as over here. There's now sort of, I mean, this should be the psi, so there's a delta x minus x prime. It's white noise in space-time, so there's a delta t minus t prime. And then it's uncorrelated, so there's a delta alpha minus alpha prime, okay? Now, the B is another matrix which simply tells me that you know, in principle, I cannot expect, if I just write it like this, that these random currents are, with respect to the component, are totally uncorrelated. You know, there could be a correlation between, you know, I've just written down these physical fields. I mean, there could be a correlation between the momentum and the energy current, right? I mean, so this I don't know yet, right? I mean, so I simply want to leave that B at the moment sort of open. Now, what is the condition which I have, what this noise should do for me? Well, what this noise should do for me is that, you know, it has sort of the correct invariant measure. It should have an invariant measure which is given by this formula up here. If I would look at this equation, you know, of course it has many invariant measures, and I just simply impose this as initial condition. Now I want to make it a little bit better, that actually this equation has only this as my invariant measure. And this is sort of ensured, and so the way how you have to do this is that, you see, you want to sort of somehow encode this matrix C, and the way how you do this is sort of by dissipation fluctuation relation. And in my notation, this sort of boils down to CD should be equal to, so these are all 3 by 3 matrices. You see, I mean, they all, of course, depend on the background value, but they do not depend on U. And so this should be B times B transposed. Okay. And now you can sort of, so D is a diffusion matrix. So in general, it will have negative entries, right? It doesn't have positive entries, but what is sort of required for the stability of the system, that it must have positive eigenvalues, right? I mean, that I definitely agree. But in general, it will be, again, in all this game, I mean, these matrices have never any reason to be symmetric, and they are not symmetric in general. I mean, so let's have a look at what they look like. I mean, so let me write down the B. Well, so if you, well, you don't remember, so I have to write it down. I mean, you look at your first equation, which was a true exact equation, was minus ct of, okay, now I've written down the continuum, but it's also in the discrete case. So you see that the current of the R field is itself conserved. So there cannot be any noise here. I mean, you know, this is an identity on the microscopic level. And so this term must be zero. Okay, and then this also sort of, you know, because it's a covariance, implies that all these terms have to be zero. Okay, and now I put in sort of some noise sigma u for the u field. I mean, that's sort of the noise strength of the momentum current.
T of u alpha.
What is that? Ah, okay. Thank you. Okay. And then there's also a vector over here. Yes. Thank you. This is 3 vector. Okay. So now I think we have everything in vector notation. Okay. So okay. So this will be okay. This will be 0. And now I have something which is for the energy. So that has some other parameter which at that stage I don't know. Now these are different. You know, they have different properties on the time reversal. I mean, that sort of forces these things to be 0. So this is what the B matrix looks like. And of course, at the moment, you know, it's just sort of an ansatz. I mean, you know, I don't really know. I don't really know the D, and of course, I have this relationship. I know the C, but at the moment, it's just an ansatz. And it depends, then, you know, as I continue, whether eventually I will find, you know, what the sort of a correct formula for the D would be, or whether it sort of maintains sort of like an ansatz, and I have to sort of think about, you know, how my final result actually depends on that choice, right? But this is something which will come later. And but I also want to write down for you the D. Now you see, once I made this ansatz, I mean, then the D is sort of uniquely determined, and if I do this computation, I mean, again, the D has sort of lots of zeros, so it has some du here sitting, which is some positive number, and it has some de sitting. But if everything would be diagonal, I mean, then you would be in trouble, because you see, then the noise would not act on the zero component at all. You know, the zero component has then somehow no coupling to the other ones. I mean, so that's maybe not such a good idea. And in fact, you cannot satisfy this equation in this way. And, you know, because the C has sort of matrix elements which sort of couple. And what you find is that there's another coefficient sitting over here, which I call this DE twiggle. And of course, since we have an underlying model, I mean, I can actually really compute what the DE twiggle is. I mean, that just sort of comes out of this equation here. And I mean, just to give you sort of an idea that, you know, these coefficients, I mean, you know, they're really computable. I mean, and they're not just simply, okay, so it's R naught. So this, okay, you cannot see this. I mean, this semicolon means that I'm looking always at the truncated correlation. So that's the second cumulant, right? I mean, it's sort of, okay, so it's V of R naught, and I have to divide it by the cumulant of R naught divided by R naught. Okay,
so that's stored in the gradient expansion of your microscopic model.
Yeah, but you see, that's one way to think about it. But you know, how to really do the gradient expansion of the microscopic model is a complicated story, right? And so at the moment, I'm just avoiding this. I'm just sort of, it's sort of a little bit sort of like, you know, I'm sort of anticipating certain results, right? I mean, of course, if you want to do a more systematic thing, I mean, then you should do a gradient expansion, right? I mean,
and then guess the amplitude of the noise from this fluctuation dissipation theory.
Yes, that's right. I mean, that's what you would hope. Okay. All right. So now we have a sort of a somewhat better equation, and now of course I can sort of now improve this equation here. And let me just write it down what I get now. I mean, so now maybe, okay, so now I have to solve this equation with this random initial data, right?
Herbert,
Yes?
when you write down, when you include the noise that way in your other equations, you are implicitly assuming the linear consecutive laws. I mean, you're assuming Fourier law.
Yeah, sure.
But we know that
Yes, correct. Yes. I cannot do everything at one step. I mean, I just sort of want to tell you what the logic is. I mean, you see, I want to sort of improve further and further, and hopefully at the end get the right result, right? I mean, so at the moment, you know, I'm still do things which maybe I have to add further words, but that's why I want to, you know, don't think so much about actually doing a microscopic derivation. I mean, it's a more phenomenological ansatz, and let's see how far we go, right? Okay, so let's see. So now I have to solve this equation with this. I have to solve this equation with this initial data, and let me just write the solution. So this is my S. Okay, so now I'm using, so this will be not the microscopic S. I mean, this S is now really the true solution, right? So S of x of t. Now, now I'm again using this terrible notation, but you know, it's not important. You know, if you don't like that notation, I mean, you know, just think of that solution. It's a Gaussian theory, so everybody in this room sort of knows how to do the solution. I just want to point out one thing. Let's see, how do we do with the minus signs here? Let's see, so this is, okay, so maybe I should write it like this. Okay, so here I have this operator which is appearing on this side, right? I mean, so it's a minus dxa, and then it's a plus dx squared a times t. And there's the c, and you know, everything down here. Okay, it depends on x and t. So let's see, I put a minus sign, I put a plus sign, I put here, let's see, no, this is okay. Okay, so let's see, what did I do here? Yeah, I think that's okay. Okay, so this is now the correct result, right?
What about the
B matrix? The B matrix does not appear in this solution. The D matrix appears in that solution. Thank you. The B matrix does not appear, but the D matrix does appear. Okay, very good. Thank you. Okay, so now I have the brackets. All right. Okay, so I think that's okay. All right. So now we have that solution. So now I want to point out one thing about the solution. You see, so now you would like to say, you know, what does the solution look like? Now, this is sort of slightly more complicated, and I want to point out one very important mechanism, namely, which later on will be also true in the nonlinear theory. You see, I mean, the D and the A, I mean, you know, they're somehow sort of badly correlated. And if you sort of want to solve this equation, you don't really, you know, if you're just there at this, it's not completely obvious. And so you have to do one thing, namely, you see, this is the first order derivative, and there's a second order. So this one is actually the dominating term, and this will be the correction. And so in order to bring this out, it's very useful to go to a new coordinate system, which are usually called normal modes, where I actually make this operator linear. And then the long-time asymptotics of that solution becomes very transparent. Okay, so let's do this. I will not do this in any glorious detail, but
You said linear, did you mean diagonal?
Diagonal, yes. So let me introduce I. So this will be now a 3x3 matrix I with the properties. So it should diagonalize the A. So the I A R minus 1 should be equal the diagonal. So should be equals this matrix minus C 0 C, and 0 is out here, right? I mean, so that's the diagonal form of the A. And then if you do this, you still have some freedom, yes?
There's a DE, there should be a DE, right? DE tilde is equal to times DE.
Where is?
Relation between the two degrees, right? The last equation, DE tilde is equal to something times DE.
Ah, okay, sorry, yes, okay, very good, yes, okay, I missed this, yes. Thank you. Yes. Good. Okay, so if you do this, I mean, there's still some freedom of how to choose the R, and you somehow want to make it unique. And you know, once I do this transformation, you might as well transform this to the unit matrix. Okay, And so the second equation which you want to do is you want to say that this R transpose is equal to the unit matrix. And if you do this, I mean, then up to sort of trivial sign changes, I mean, the R is actually uniquely determined. Okay? So now I will not continue with this formula. I just will tell you what the result is and the reason why I sort of wanted to emphasize this. Now, you see, once I go to this transformed thing, then this thing will be diagonal. Okay? But it has 3 different eigenvalues. So what will be happening is that because, you know, they are all distinct and, you know, you have these moving peaks, what will be happening is that actually in this new representation, the 3 fields completely decouple at long times. And so, in fact, what you will see is the following picture. Is that so? Again, you know, I'm looking at okay, no, maybe I should say this more clearly. So okay. So what you will see at long time? Okay. Okay. This is something which is going to come. So let me not dwell on this at the moment. I mean, so let's think of one particular matrix element over here, and so I'm again plotting this function now for large T and one particular matrix element. And what you will see is sort of course, again our 3 peaks. I mean, that's necessarily so, and each one of these peaks is now sort of smoothened according to a Gaussian. So this width will be the square root of T. Something like this here over here. But the coefficient which tells you, you know, the diffusion coefficient which tells you the scale on which this is broadening is now are now the diagonal elements of the transformed diffusion coefficient, right? I mean, so how should I say this? Okay, so let me not introduce some notation. I mean, so all what maybe at that stage I just want to say that at large times you have a decoupling. I will do this in more precision a little bit later on of normal modes. And the reason is because, you know, these peaks are moving apart, and therefore, you know, eventually in this new coordinate system, I mean, I will have some transformed D. This D will be non-diagonal, but what I will see in this picture is at long times just the diagonal elements of this diffusion operator. Okay, so let me maybe just leave it at that stage. And now, of course, you know, your remark here, no, who's, well, someone. Anyway, so you know, the remark was that you know, if you now look at these peaks. Okay, so let's see, what do I want to say? Okay, so let's see. Okay, so let me maybe put it this way. So the KPC lesson is that okay, and why is this the KPC lesson? Well, the KPC case is simply the case of a single component. Okay, and if I write down sort of the derivative form of the KPC equation, you will find simply the following equation, CD2U. I mean, it's just a noisy Burgers equation. And there is a, well, okay, and usually in the KPC equation, I mean, you don't have, you sort of transformed already to a moving frame of reference. So the A is sort of 0, right? I mean, because, you know, there's only one single eigenvalue and I can simply remove it. I mean, here there's no frame in which I could make this 0 because there are, you know, 3 distinct eigenvalues. I can sit on this one, but then the other ones are still moving. Okay, so I can sort of leave this out. I mean, then there's the U squared, there's a minus dxu, and then there is sort of the psi, and this only is now a scalar equation. So that's the KPC equation. And there we know that if I just do the linear approximation, so if I drop this nonlinearity and compute, the covariance for that equation, then I will see just a simple Gaussian peak sitting at the origin. But we know that the nonlinearity is extremely important and relevant and will change the long-time behavior of that system. Okay, so the KPC story tells us that of course, there's maybe other ways to see this, but since we have all this sort of knowledge about the KPC, it tells us that we have to include sort of higher order terms. Okay, and so what we have to do is, and that will sort of the next chapter include quadratic terms. Now, of what? Well, you can see this from this equation. I should add quadratic terms in the Euler currents, right? So add quadratic terms in Euler currents. Now, the next thing is, you might wonder, why not even more terms, right? I start adding quadratic terms. Once I go away from the linear world, I can sort of add, in many places, I can add further terms. For instance, I can, the true D will presumably depend on the background values. And so in principle, I should also account for some nonlinearity in the U. Presumably the noise strength will depend on the background values. So if I start asking, I have to include nonlinear terms, there are many possibilities to do this. Well, there's also many ways of how to sort of argue which one should be important and not important. And so you just sort of look at terms of, you do a space-time rescaling, and you just see how, the various convection terms scale. And what you find is that the one which is dominant is indeed the one which sort of comes with the quadratic term of the Euler. So if I would take a cubic term here, then you see that, under this space-time transformation, that this will be a term which is sort of marginal relevant, and for our purpose at that stage, sort of, you can just think of it completely irrelevant. You can look at variations in D and do the first order correction, and then you see that it's again at that scale sort of a term which is not relevant. And so since it's complicated anyhow, once you do the simple sort of dimensional analysis, you discover that you definitely should first take this one into account. All other terms will be of lower order compared to the U squared. Yes.
The APC has a non-conserved noise in it. Here,
no.
Conserved noise.
Okay, good.
So the Edwards-Wilkinson actually, here it's Edwards-Wilkinson.
No.
Is it no?
Sorry.
Becomes incorrect.
No.
Maybe it is no, but I don't
No, it's fine. So this is the KPC equation, right? Now, its gradient form is U is equal to dH of x. So I look at the dynamics of the slopes.
Oh, you just differentiate. So I
Okay,
understand.
and now when you just write it down, you see it's really an identity. That is really just the same thing, right? So no, we're really sort of, we're looking, maybe it's slightly different variables, but we are really exactly on the level of the KPC equation, right? Okay, so now let's do another small thing, namely let's look very quickly at the discrete nonlinear Schrödinger equation. And what I told you was that in this case, the A is equal to 0. So there are no nonlinear terms. There is, there's not even a linear term. It's not a quadratic term. Okay. Well, so then you say, okay, then we have a theory which is exactly of the same type. This term is simply 0. Well, then, at that level, you would say, aha, this funny KPC convections, they are simply not present. And so you would think that should be actually the correct answer. Okay, so if I do, now we have two components. Both components have, it's energy and density. Both components have the same transformation under time reversal. So there will be a non-trivial D matrix. In fact, numerically, you can compute it. You find indeed it's fully occupied. It has some negative entries actually also, but it has positive eigenvalues, and there will be some B matrix which you then can compute on the basis of this relation, and that's it. Okay, so for the DNLS, if I follow that scheme, you would conclude that this picture of Gaussian peaks is correct. The only thing which you have to remember that, and then there are zero velocities, there will be non-trivial correlations between the two components, and that's it. So I just have a two-dimensional sort of two components. So, for each component, it's sort of a multivariate distribution. You just have two random fields, and they jointly have a Gaussian distribution, okay? Now, numerically, this comes out very well as long as you make the temperature sufficiently high. Okay, and what else happens? That's a different story at the moment. But I just want to point out that you can apply this simple sort of idea to DNLS. And, with some provisos, you actually get a very good answer. Okay, and then once you're at that stage, then, of course, you realize that D can be written as via Green-Kubo formula, as a time integral. Of course, you cannot compute it, because you have to know the dynamics. But then these things are no longer phenomenological. You could actually write down formulas which sort of actually are sort of, the true microscopic value of the D. Okay, so then you can sort of support such kind of a somewhat phenomenologic picture actually by true microscopic expressions. Yes.
The modes happens only when you include nonlinear.
No. You see, this is what I was trying to say. Let's see. No. But I was trying to say the decoupling you can see already on the level of the linearized equation.
So after you transform, the D is no longer diagonal.
Yeah, if I do this R transform, which I will introduce in a second more explicitly, then the transform D will be not diagonal, not at all. Because the R transform is made to make A diagonal, and then there's no reason why it should make D diagonal.
But then wouldn't they be cross correlation?
Yeah, sure, they're cross correlation, but these cross correlations, even at the Gaussian level, they just disappear because the modes are separating. If the modes would sort of sit on top of each other, then of course there's no mechanism of sort of becoming independent, and that's just what happens in the DNS case. Then it's just some 2 by 2 thing, and then that's it. Okay. All right. So now I have to include this quadratic Euler things, and let's see. Okay. Is that still visible, or is it too far off? Okay. So maybe. Okay. Now. So this is quadratic Euler. Normal modes. Okay, so I told you more or less, what we have to do. So maybe I don't have to write too many formulas. So let's maybe just write down the current. Okay, so I had AU was the linear one. Well, and then I just get second order. So I get I get 1/2. Now I get something which must be quadratic in the U. So I write it as U vector, and then there will be so maybe I write it like this: component alpha. Now second order will be a Hessian, so there will be a 3 by 3 Hessian, which of course depends on the component times U. Right? So this will be now the corrected current, right? And all the other terms stay the same. Okay. So again, this Hessian is a 3 by 3 matrix. It depends on the background values. It's just the second derivative of the Euler currents at that background value.
In a sense, it's a 3 by 3 by 3 third rank tensor.
Okay, if you want so, yeah. Okay, so the way that's fine. Mm-hmm. All right. Okay, so now we have to do this normal modes. So I have already introduced the R matrix, which has a normalization and which diagonalizes the A. And I have to sort of introduce some symbol. Let me just call them phi here. I simply transform my U field, which is sitting up here, to a new field which I call phi. This is just a 3 by 3 matrix, so it's not depending. It's not acting on the x variable. Okay, and it's a given matrix. It's sort of computable matrix once you give me the potential. Okay. Well, so now I have to do all this transformation. So let me just sort of do this a little bit. So if I take the R sharp, which is, you know, the transformed A. This I had already. This is a diagonal of minus C0 C. And of course, now I have to transform all the other things, right? I mean, I get the D sharp, which is the transformed diffusion matrix. I mean, this is the one which I didn't want to write down before. It's the diagonal elements of this matrix which will sort of determine, you know, the scales for each one of these peaks. I have to transform the B. I mean, the B gets transformed into, the B sharp gets transformed as RB. Well, let's see, what else? No, I think that's all I have to do. And now I simply have to rewrite this carbon in terms of these new objects. And then I get an equation which looks like this, ddt. Let me still write it down, I mean, plus dx. Okay, and now I have a transformed carbon. It's equal to 0. Okay, so, well, what do I have? Well, I mean, now here I have, this term is now linear, right? Because I mean, this has it's not a matrix, it's just sort of a scalar here. So C alpha, I mean, you know, alpha goes through the 3 components, and then the C alpha takes these values, I mean, minus C0 and C. Well, then there is the diffusion, no, then there is the nonlinear term, which I write as phi. So, you know, I get, you know, after doing this transformation, that will induce the corresponding transformation for the H. So there are new coefficients, which I call G alpha, phi. Well, and then the other terms, that, you know, I get the D sharp, dx phi alpha. Well, okay, so dx, D sharp alpha. And of course, I get the B sharp times, again, white noise, because I mean that I have not really transformed. It's the same white noise after transformation. Okay. So if you want, so these are really the objects, you know, in which we should do some analysis, right? And the analysis is that, I mean, remember that these C's are distinct. These are sort of the nonlinear coefficients, and then there is noise and dissipation. Okay. All right, so now let me sort of, I mean, just to make clear what the logic is. I mean, I said this already, but I said I should have said this presumably at the beginning of the lecture and not in the middle. But anyway, I mean, so let's first see what we do. So now we have, of course, a nonlinear theory, so we know much less, but nevertheless, I can sort of imagine that, you know, it has a steady state. You know, it's a complicated system of coupled partial differential equations. So of course, I don't know very much about it, but I can imagine that, you know, there's a steady state solution. So I look at the steady state. And since we do linearization, since we do linearization, I mean, you know, we might as well assume that the phi variables have average 0. And then I can now look at the correlator, alpha prime, and let me do the sharp, because this reminds me that I'm looking here at the normal modes, and that's of course the standard thing. I mean, it's just the phi alpha field at the point xt correlated with the phi alpha prime field at 0, 0, right? I'm using again stationarity, and so this is the thing which there are questions. Well, equilibrium, I don't know yet. I mean, you know, let's say stationary state of that equation, right? I mean, you can call it also equilibrium. You know, what I have to do is I have to, you know, I have to study this equation at that stage.
But if your S is that kind of
in the steady state, in the steady state. I don't know. I mean, you know, you might want to call it equilibrium. That's fine. But you know, at the moment I have this, you know, anyway. So, okay. So if you want to like it, call it equilibrium. I mean, you know, you can also call it equilibrium. I mean, it's a stationary measure of these partial differential equations.
Are you implying this could apply to a driven system where?
No. I'm looking at this. I'm looking at these equations, right? I mean, so you see.
Are there applications of this where it's a non-equilibrium state?
Well, in principle, you know, this whole theory, I mean, is not restricted to thermal equilibrium, right? I mean, I mean, I don't think there's been any sort of serious studies, I mean, to do this for non-equilibrium steady states. But in principle, it's not, it just hasn't been done really, okay. Okay, so if you... that's right. I'm sorry. Yeah. Okay. So Henk is correcting me. In fact, I wrote a paper on that myself. Okay. So thank you. Okay. Yes. Absolutely. Okay. Okay. So let's see. So okay. So this is the correlator. Now, of course, at the moment it's just a definition, and in fact, it's not even clear whether it's well defined. And you know, I would have to work on this a little bit more in order to see, you know, whether I can make any prediction. But I want to bring out another point. I mean, so let's assume that we have sort of computed this correlator. Now, what is the claim? What we are doing? I mean, so you see, you have this R transformation, which just is a 3x3 matrix. Now, this R transformation I can easily apply also to the microscopic system. You see, instead of looking at the physical fields, which I had intended originally, which is all the natural field, I can look at particular linear combinations of this natural field, and these are the normal modes of the microscopic system, right? And so I have another object which I can look at, which is not very much distinguished. It's just sort of, you know, the same thing as alpha. It's also the psi, but now I put here the J somehow to remember that's from the microscopic system. But when you look at the definition, you know, I just have to do this V vector, and then I have to take the alpha component, and then I have here J and T, and then I have to correlate this with the same V vector at alpha prime at 0, 0. And of course, you know, here I should always do this you know, truncate this average, okay? Okay, so this is now, you know, the normal mode transformed correlator of the microscopic system. And of course, you know, somehow the hope or the claim, let's put it more positively. So the claim would be that the S sharp is sort of, you know, approximately, okay, the S sharp of X and T, so the continuum S sharp in some sense for large X, for large space separation and for large times, I mean, it is sort of the same as the one which, approximately the same as the one which I see over here, right? I mean, so this is somehow what is in the back of my mind, that you know, if I would be able to compute this correlator, presumably, you know, not an exact solution, but somehow approximately for large X and T, then I could actually sort of see directly what's happening in the microscopic system.
You just need large time. Because as long as you're at large time, it should be fine at all.
Well, that's not so. No. Well, not. No, I think. Well, you know, I mean, for instance, if I want to capture the sound peaks, you know, I need large X, right? I mean, you know,
no, but if you're at large time,
yes,
it's valid for large X as well as at X equals 0, right? So it's got a heat peak right as well.
Yeah, that's right. Okay. All right. Maybe yes. Mm-hmm. Okay. Are there restrictions on?
On G, because you have to eventually.
No. You mean on this one?
Yes, because something like the fluctuation dissipation.
No, I know. You see, on the G, I have no choice at the moment. You know, I mean, the G, you know, the H is fixed by the model because I just do the Hessian, I do the transformation, so the G is whatever it is. No restriction. Well, I mean, there's a restriction. You will see there are actually restrictions which come from the model, but not when I write down these equations. I mean, you know, the G is I mean, you know, I take the model, I compute the current, I compute the Hessian, I do the normal mode transformation, and it pops out the G. There's no choice. There's no freedom whatsoever.
And I think also you don't want to impose deep thermal equilibrium because you say you want to apply this more generally.
Oh, okay. So yeah. No. We want to apply this. I don't want to apply this to anything more general. We want to apply this to the anharmonic chains in equilibrium, right? Okay.
So the long time limit is automatic. So the long time limit of this is automatic.
Yeah, that's okay. I could have said stationary. Maybe that would have been a better way. Yeah, the long time limit. You see, the trouble is, I'm sort of maneuvering here back and forth a little bit because so maybe I should make this as one explanation. You see, if you look at this equation here, we know what the steady state is. It's just delta correlated in x, which is of rather natural steady state. The reason why I'm sort of maneuvering at that level is that for this equation we don't have that information. It's too complicated. I mean, we don't know what the steady state is. We don't know what the equilibrium state is. In some cases we do. This is a separate story which I don't want to go into. I just sort of want to say that at that level of the discussion, I simply wouldn't know what the stationary measure is. That's one of the difficulties, sort of, it's a subtle difficulty. Therefore, I don't want to overemphasize this. But the point is that it's a big difference between one component and several components. That in this case, by coincidence, by luck, but as a matter of fact, is that we do know the stationary state. Right here, we don't. In general, in some cases we do. So it's a slightly complicated story. So I don't want to enter this at that moment. And rather, what I want to do is I want to let's see. What do I want to do actually? Yeah, this is fine. Okay, so that's already the end of that particular chapter. And the next thing what I want to do is I want to introduce sort of these two types of techniques which one can use in order to actually try to say something about the system. And you see, it's not really, there's a lot of room for improvements. That's all what I want to say, right? And so I will just tell you the two things which have been actually carried out, and which, of course, are important to be carried out. Otherwise, it would be more like an empty scheme, right? If we wouldn't be able to say anything about this equation, I wouldn't give the lectures, right? The point is that we can say something about the equation, and we can try to check whether the thing which I raised over here is actually correct. Anyway, so the next chapter is decoupling. Yeah, just one moment. Mode coupling. Sorry, I'm listening in a moment. I'm interested in mode coupling. Okay, and now what is the question? We go to the right. Okay, sorry. Okay, I have to raise again. I wrote it down very carefully. Okay, so let's do the chapter 8 on so it's called decoupling and mode coupling. So these are two very different arguments. So the decoupling is sort of something which I told you already. Namely, you simply argue that when you look at long times, then the modes decouple. And I'm already in the normal mode representation. So I simply say that I can simply drop all terms which couple different components of phi. Okay. Now this is not the correct decoupling. This is a little bit too naive. But this is what we did in for the linear case. Okay. So it was decoupling and mode coupling. Okay, so what do I have to do? Well, you see, here there are these coupling constants. And some of them are important and others are less important. Okay, now that, of course, you just sort of, we did a lot of numerics on sort of related things, and so I have some confidence with that, and but it's sort of more like an assertion. So now what we observed is that if I look at this particular, okay, so I look at one of these G alpha matrices. So here it's maybe, so let me just do this sort of. So here's one of these G alpha matrices, right? And so what we say is that the couplings which sit on the diagonal, so they have two equal indices down here. They actually are very important and determine the long time behavior of the system. Whereas, these ones up here, they are not so very relevant. So I can change them. I shouldn't change too much. So now I'm talking about this decoupling. So now I look at this thing and I want to decouple. So let's assume that I want to decouple one particular component alpha. Well, if I decouple, then of course, the single component will just look exactly like this equation. Right? I mean, that you know, if I drop all the couplings in this, I mean, I fix alpha, and I drop all the couplings here, then it's just that equation. The only term which is different is this one, but that's just a constant translation.
But what about the T?
It's the same. I mean, I drop all couplings. Okay, I just drop everything. Okay, except for the ones which have the same component. And then I get, of course, you know, once I decouple, then I just get the one component system. Okay, if I have a coupled system and decouple, I get the one component system. That is the one component system. Okay, well, so it looks maybe not such a bad idea, but you see, there's one caveat. You see, it could be that the term in front of this thing here is actually zero. I mean, that's, you know, I mean, the g's are whatever they are. I mean, I just don't know, right? So it could be that the g alpha 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 is actually zero. Then you see already, you know, of course, you can still say, okay, I do decouple, but you know, the answer is nonsensical because, you know, then I see a Gaussian peak, and this is clearly what we, you know, don't really expect. Okay, so the correct decoupling assumption is the following. We sort of, you know, rely somehow on saying that you know, they're already that. Okay, so the correct decoupling assumption is the following. That I'm using here implicitly that the velocities are distinct. So it's just in this case. So if G alpha alpha is different from zero, then so is G alpha alpha equal to zero? Well, okay, so for this, you have to actually compute these coefficients, right? I mean, otherwise, you know, you cannot do. And the answer is the following. So, in fact, so the heat mode you cannot decouple because, you know, this condition is definitely violated. Now, generically, which is equal to minus G1 minus 1 minus 1 minus 1. So I labeled here the modes according to the eigenvalues. So minus 1 is the mode which corresponds to the left going, and plus 1 is the one going to the right going. So I just always go along the order of the eigenvalues. Okay, so this in general will be different from zero. Generically, I mean, so there are cases where it's actually zero, but that's sort of an exceptional situation. So this means what we can do is sound modes decouple. Okay, and so this is telling us that the S of alpha, I mean, under this decoupling, it tells us that. Okay, that okay, that okay, that the S11 of x and t. Now I'm sharp because I do this in normal coordinates. Well, I mean, if it decouples, then if it decouples, I mean, then you know, I can use the fact that for this equation we do know the stationary covariance, and so we have a scaling form which tells us that this is equal to some coefficient which one can compute to the minus 2/3, and then there's a scaling function which is also known, which is not a particular spectacular function, sort of symmetric function, and then sort of decays with x to the stretch exponential is e to the minus x to the 3/2 decay. So it's a nice localized function. And well, I mean, you know, we said that things are normalized. We said that the integral, that's the first sum rule of this thing, has to be independent of t. But you see, I normalize things. So when I do this integral in x, I mean, this is exactly equal to 1. So there's no factor appearing here. But these things, the FKPC function is normalized to 1. So, you know, this volume factor has to sort of, I mean, that's just the volume factor, but the true scaling is x. Now, it's x, and now I have to remember that I'm looking at the white sound peak, so it's minus CT. And then you have to divide it by the same factor over here. So it's lambda ST, the 2/3. So we made one prediction, namely that if we now look at the long time behavior of, if I assume that I can really identify this with the microscopic model or take this as a prediction, then the prediction would be that if I look at the sound mode for long times, it should sort of have that very particular scaling. There's a scaling exponent 2/3. I mean, there's a scaling function, which is explicitly, it's tabulated. And there's a non-universal coefficient. It's only that coefficient which still depends on the particular model which I'm looking at. But the lambda s, I mean, is actually known also because it's particularly simple. In this case, the lambda s, this coefficient, is nothing else but 2 times square root of 2 times G11. Okay. All right, so this was the easy case, right? I mean, it's far from any proof, right? I make this decoupling, but it's a valid prediction, and well, Abhishek did lots of simulation. Other people did also lots of simulations, and there would be a total another story to say how well this is sort of confirmed. But I mean, it can be seen, right? I mean, there is good numerical support for that type of conjecture. Okay, so now what do we have to do? Well, I mean, so the next thing which I want to do is just a moment. Peak. I mean, here there's still a question mark, and so here I have now the sound peaks at CT and at minus CT, and for them we know now that they're KPC and this goes like T to 2 cells. So this is how far we got, right? And so the question is, what do I do about the heat mode? Okay. Now we don't really know what to do, but there's sort of one sort of fairly generic technique for such kind of Langevin equations or sort of stochastic field theories. You do something which is called one loop approximation or sort of mode coupling to lowest order. Now, of course, I will not go into this at all. But I want to give you at least sort of a slight flavor. I mean, basically what you try to do is you try to write down sort of an equation for this correlator. And so you do essentially sort of perturbation theory in the quadratic nonlinearity such that the correction term is of quartic order in the phi, so it's really second order. Okay, and at that, I mean, you have to do this correctly, but in any case, and at that level, you have sort of like a fourth order correlation, and you simply do a Gaussian decoupling, and then you get a closed equation for the 2-point function. Okay. Now, I'm not going to write down this thing in general, but in a somewhat simplified version, because you just get a long formula, and if you see this for the first time, I mean, it's not very instructive, and it's not needed for what I'm actually want to do. I mean, so first I do mode coupling, and the second thing is that I use a diagonal approximation, which sort of seems to be pretty good. I mean, I do mode coupling, and what I said before, I mean, was maybe more precise. I mean, what I wanted to refer to is that we did a lot of simulations on the full mode coupling equation, and we saw that this diagonal approximation is actually pretty well verified. Okay, so now I'm talking already about mode coupling approximation, and this simply says that this S alpha alpha prime of x of t in mode coupling should be approximately diagonal in the sense that I have a delta alpha alpha prime and then some function f alpha, which of course I still have to determine, of x and t, right? Not really, I would say. I mean, there's some vague connection, but it's certainly not a function which, you see, for the Tracy Whittem, I mean, that's a function which was discovered by the random matrix people, right? I mean, this was discovered by the KPC people and has now had never appeared before in random matrix theory. I would say it's not really connected to random matrix theory. Yeah, no. Okay, so this is the diagonal approximation, and you see that that's already consistent with the result which I claimed here for the heat peak. So if I take here the 1,1 component, then we know that the F1 and the F minus 1 is exactly, you know, this function sitting over here. Yeah, I mean that was sort of the decoupling, but the goal is now to actually compute also the one with the index 0. I mean the heat peak. Okay. All right, and so now what I'm doing, I'm going to write down for you this mode coupling equation in the case, not in the general case, but under this diagonal approximation. And I mean, I'm writing it down because, you know, otherwise it sort of really would come out of the air, and you know, you have a hard time to understand what's actually going on. Okay, so let's see how I do this. Well, I mean, you know, you have some equation for the full 3x3 matrix, and then I just plug in this particular form. And I'm going to write it down actually in position space, I believe at least. Yeah, I'm going to write it down in position space because there's one particular feature which is sort of more easily seen in position space. So let me write down dt of f alpha of x and t. Well, so first of all, there are sort of the obvious terms. I mean, there's the minus c alpha. I mean, the shift f alpha, and then there's some d alpha, some diffusion coefficient, which comes also from the equations. Okay, so this is sort of the free part, which of course you have all the time, right? Okay, now there will be a more complicated term, which comes from the interactions. So and there's an integral from 0 up. So it's a memory type term. There's an integral over ds, and then there's an integral over dy. Okay, now I see the same function f. I mean, but it displays arguments. I mean, so it will be a function of x minus y times s. So that's somehow, in fact, I think it's presumably t minus s here. Okay. And then there will be, so this is still alpha, and then there will be sort of a memory term, alpha, which depends on y and s, right? I mean, so this is sort of the structure. I mean, so you think that, you know, this interaction sort of somehow have some influence, and after they had some influence, I mean, they're still propagating according to the full propagator up to this time s, right? I mean, that's sort of the structure. Now, of course, the question is, what is this MML, this memory term? This also comes out of the mode coupling. I mean, so the M alpha of well, I wrote it in x of t, but you know, you have to plug it in here with the correct coordinates. So it's a factor of 2. Then there's a summation over gamma prime equals all modes 0 plus minus 1. And then there is a g gamma prime. So these are these coupling coefficients, alpha. Because we do second order, they come in quadratic. Okay. And then it's just quadratic in the two fields, or in these two scaling functions, if you want. So f gamma of x and t, and f gamma prime of x and t. So this is the mode coupling, right? Okay, so okay, so now there's one additional observation is that you see, I mean, these modes travel with different velocities, and so if I take this index different, the gamma different from gamma prime, I mean, they will sort of separate. And presumably, you know, they will have very, very small overlap. If I wait very, very long, I mean, they are really very far apart. You see, I imagine sort of these functions f. I mean, if you look at this formula, that you know, this picture, that they are sort of centered at you know, the 3 peaks which we know, right? And so if they are very far separated, you would think that, you know, whenever these indices are different, I can actually really drop them for long times. Okay. So now the question is, can I do anything? So in fact, So here with only gamma equal to gamma prime.
That's the diagonal approximation.
No, the diagonal approximation is saying that this full matrix will be, for large x and t, will be approximately diagonal. That's one, you see the full mode coupling equations have a similar structure than sitting over here, but all these objects, here I have sort of, just scalar functions, but all the objects are actually 3x3 matrices. And so the full mode coupling equations look a little bit more complicated. Of course, they have the same structure, but there will be more indices, and then you will not just simply have this g squared. I mean, it's g times g, and with all kind of indices floating around. And so if I just do if I do the diagonal approximation in mode coupling, I will get exactly this equation. And it's just remarking that on that level, I can very easily see that only terms with gamma equal to gamma prime actually contribute. Okay, so now let's do the heat peak. Well, I mean that's sort of fortunately not very difficult. So now I want to do alpha equal to 0. Okay. Well, there's the term G alpha L. I mean, G0, 0, 0. This is always different from 0. Sorry, that's exactly equal to 0, right? I mean, that's this term over here. So you see the only terms which actually survive are the terms G1, 1, 1, let's say, and then I have F1 squared, and then, of course, there are sort of the corresponding other terms, right? I mean, sorry, 0, okay, and then there will be also the term G0 minus 1, F minus 1 squared, right? Well, now I look at this equation, and what I realize is that, we have already argued what the F1 and the F minus 1 should be. Well, I mean, it's sitting right over here. I mean, it should be just the KPC scaling function and shifted, I mean, to the right and to the left. Okay, well, so you see, I mean, this equation, which looks very nonlinear, if I know already what these functions are, and I do, then I can just plug them in over here. Now I have a linear equation. Of course, it has a memory term, but it's linear. You see, this is linear. I mean, that's a linear structure. That's a function of alpha. But this memory kernel, I know, right? Because it only depends on the two sound modes. I mean, it doesn't couple to itself, and so it just sort of depends on the two sound modes. Okay, well, I mean, then I have a linear problem, which hopefully I can solve. And let's see, I have to sort of think about how to do that. Yeah, okay. Okay, let me maybe actually do one thing here. I have to watch out for my time. Okay, let me maybe do it this way. I mean, so because otherwise sort of looks a little bit up in the air. So I have to study this equation, and there's one result about this equation is the following: that okay, let's do this. I mean, for a second. I mean, let me maybe write this in Fourier space. So and let me drop the index alpha now. I'm just looking at one particular problem. So I have, let's say, this function of k and t, and I'm dropping these terms. I mean, they don't play any role. I just keep this one here. So actually, there's an error. I mean, there's a second derivative sitting here. Sorry. So there's a minus k squared, and then of course there's the memory term integral from 0 up to t. There is ds. I mean, there is this function f of t minus s. Well, because the long-time behavior, it will play no role. I mean, yeah, that's right. I mean, so I can drop the diffusion here. Okay, and so then let me say that these are sort of these known functions. I mean, so there's a g hat of g. Now it's product in x space, so it must be convolution in momentum space. So I put here the convolution. And of course, what was convolution before is now product. I mean, so it will just have that particular structure. Okay. I've just written down what I was trying to say in words. That I know these functions. So this is known. And the f I want to compute, right? And now the result is the following. That assume that this function is of scaling form and has a dynamical exponent c. Now in our case we have a particular value of c would be 3/2, right? But I mean let's simply assume that the function which I put in here is already of scaling form. And then let's look at the long time behavior and let's ask what does the solution look like? Okay, and the assertion is that the f hat of k and t as a long time solution of this thing is actually a stretch exponential. Namely, it's given by, up to some factors which I leave out now for the moment. There's simply some scaling factor in here with a new dynamical exponent, which I call c tilde. And the relation between the c and the c tilde is that the c tilde is equal to 1 plus 1 over c. Okay? So that's the result which you can check.
You said stretched exponential.
Well, because I have here, and it's e to the some power which is not 1 or 2. So this I just call this stretch exponential. Okay.
Not power in t.
Yeah. Okay. So now I can apply this to our.
What was intended to apply large k or small k or small?
No, if I do this type of approximation, it's large t and small k. It's just the usual one, right? Small k. Well, it's large distance behavior, right? It's always.
The argument up in the exponent is large or small. The combination, or
No, the combination is of order 1, right? This is order 1, and then so small k, large t. That's sort of okay. All right. So this is very fine. So let's compute the c tilde. So now the c in our case we know already is 3/2, right? That's the KPC scaling function, and so the c tilde. I hope I did this correctly. Will be equal to 5/3. Now, if I apply this to this case, the non-universal coefficient which is sitting here, which determines the time scale, is something sort of slightly complicated. It's an explicitly known coefficient, but I simply don't display it, right? Okay, so you have this result, and then what do you conclude from this? Well, you conclude the following: that you say that this must be the scaling function for the heat peak. Okay, so what we find is that the heat peak, which was the f0, now I write the Fourier transform of k and t, is again up to this time scale which I'm omitting is e to the minus k to the power 5/3 times t. Now, I really would like to look at this in position space, because this is sort of my physical intuition, and that's where I drew all the pictures. And so now I want to fill in what is this question mark actually. And if I do the Fourier transform backwards, that's at least the probabilists in this audience know this immediately, and everybody else presumably has seen it also. This, if I transform backwards, this is what is called the Levy distribution, right? So this is Levy 5/3. So it's unfortunate that that's a stable law, and in stable laws, the Levy distribution are characterized by 2 parameters. They're called alpha and beta. But these symbols I have used already anyway. So it's the Levy distribution with alpha equal 5/3. The Levy distribution with alpha equal to 2 is the Gaussian, and then you have all these other Levy distributions, and this is the one which is 5/3. Okay, now what does it look like? Well, it looks the following. You see, it has a singularity at k equals 0. So it will have a slow decay. And in fact, it will look something like this. And that's something which in the numerical simulation, if you know, any one of the predictions, you might wonder, you know, which one are you going to see first? The one which you're going to see first are these power law tails of the heat peak. So, you know, this looks something like this. It's a distribution which doesn't have second moments, actually. Okay? It's a Levy, so it goes down like this. Okay, and this decay is here like x to the minus 8/3. So the mechanism how you should think about this interaction is that, you see, if this would come out to be a short-range function, then you could physically not understand what's going on because, you know, this is sitting over here, and how possibly could this interact with a sound peak which is way on the other side? But since it is a power law, and then you compute, you know, what's happening, how big the field is, you know, at the sound peak, then you see that everything just matches, and that this small tail still can interact with the KPC peak. Okay? There's no, you know, there's no back reaction. So I mean, the nonlinearity of the KPC peak is so strong that there's no back reaction. So to leading order, it really looks like the KPC peak. But since here the leading term is vanishing, you know, the G0, 0 is 0. It's the back reaction, and this is what the back reaction produces for you. Okay. Let's see now. Yes.
I guess the power law should probably stop at the.
Okay, so I just wanted to mention that. Very good. Thank you for reminding me. So now you go further out here, right? I mean, this is sort of further out. And then, you know, then you sort of suddenly, you know, if you simply imagine to continue this mentally, you see that cannot be correct. I mean, because I mean, you cannot have sort of slow correlations outside the sound cone. So in fact, what you see in every simulation is, and of course what should be the correct answer is that once you're here, yeah, of course that's slow power law, and then it's simply cut off by the sound peak. And out here you sort of see, you know, very, very small correlations. And that's another sort of, which I personally think, you know, it's not a very deep prediction, but it's somehow, you know, sort of supports the theory that for instance, this detail, I mean, it really gets completely right. You see, it's a sort of very qualitative, it's saying that, you know, nothing of the structures that's saying outside the sound cone, I see no correlations. But that's sort of nicely reproduced by that theory, and that sort of, you know, tells you indirectly that there is some substance to it. I mean, that's, of course, a much, much more detailed prediction. Yes?
Outside it should be KPZ tail, right? Outside it should be KPZ tail, right?
Yeah, okay, but you know, this function, as I said, I mean, you know, this function goes like e to the minus x to the 3/2, if I remember this correctly. And so this, of course, it goes very quickly down. So out here, I will see no correlations whatsoever. Okay, well, so that's what I wanted to say at that stage. And my time is almost up. And so maybe actually...
And the width at the middle of the peak is t to the 3/5.
the middle of that peak is t to the 3/5. You know, once you do the Fourier transform, this power law gets inverted, right? Yeah. Okay. That's right. So this is so if you want, so this is sort of the final picture. Not quite. I mean, we know more details, but I mean that's sort of one of the basic results of this sort of whole nonlinear fluctuating hydrodynamics, and it's this picture which you can actually compare with numerical simulations, which I will not go into. Since I have sort of 1.5 minutes. I've prepared a few other things, but this I think I will not be able to say. But let me say one thing, which yes. Yes. But you cannot know. Yeah. Well, no. This okay. So yeah, but that's. I repeat, at least I repeat the way I understood the question. I mean, so this has nothing to do with many components, already a question on the scalar case, right? I mean, you know, your question applies also to the scalar case. So let me try to explain in the scalar case what the situation is. I mean, so this is a u squared, and then I have a minus dx. I repeat the question, then is equal to 0, right? And what your question is why don't I drop this noise term? Is that correct? okay.
the
So,
noise and dissipation to 0 in the right ratio, so the steady state stays the same.
oh, okay, you want to take it to 0. Well, I mean, okay, I mean, okay, so maybe I can say it like this. I mean, so suppose you take this equation here, right? And now you simply do a scale transformation by, you know, going to larger x and larger t. And if you do that scale transformation according to, you know, the 1/3 and the 2/3 of the KPC equation, then what happens actually is that this term, under this scale transformation, this coefficient is order 1, but the prefactors of those actually goes to 0, but in such a way that the white noise stays constant. I mean, is still invariant, right? I mean, it goes jointly to 0 so that the white noise, which is a stationary solution, always sort of remains intact. No, I mean, okay, okay, yeah. So, no, what I'm saying is that, you see, at very long times, everything is dominated by the quadratic term. But this noise is needed that you have sort of the correct local structure. You see, you have sort of two scales here. I mean, sort of, you know, if this is the solution, then on a small scale, you will see sort of like white noise behavior, which is enforced by this term. But then, you know, if you ask about the fluctuations on a much larger scale, it's dominated by the u squared, right? Okay, so I want to do one thing which is maybe also new to the experts, and some people might, and I can explain it in a few minutes. I mean, it's sort of a generic question, and I have all the things which you need for this. You have already here, and question you might ask. So let me do this as a last point. So this is number 9. This is the dynamical. I guess David had this word also already, my dynamical phase diagram. Okay. So what do I mean by this? I mean, so, you know, at some point I said something generic, and then this is what you will see. And so the question is, do you always see it? You know, I vary the potential and maybe also the thermodynamic parameters, and the question is, I mean, do you see that, right? I mean, what do you see, right? Okay, and so this fortunately has a sort of a very, very simple answer, and so I can explain this in a few minutes. I mean, so first of all, the relevant couplings I claimed already that are of the form where I have two equal lower indices, okay? And the other thing which we know already, that the G0, 0, 0 is equal to 0. And there's another information which you need, which again, you know, it comes from the anharmonic chains. I mean, it's a property of the microscopic model, namely that the G0, 1, 1 is actually always strictly positive. And so if I look at the coupling of the heat mode to the other ones, you have a matrix which I'm only interested in the angle. I mean, here's the 0, that's this one, and then there is sort of here a positive term 1. And here a minus term, and this, you know, whatever. I mean, you know, they don't play any role. I mean, so this is my structure. Okay. Now the G1 and the G minus 1, they are sort of reflection of each other. So I just have to look at the G1, 1, 1. Okay, and so this is sort of the relevant term, right? I mean, this is the self-interaction term here. Okay. Sorry, this is the one matrix. And the relevant interaction term is this one. And what I said is that G1, 1, 1 is different from 0, but I said generically. And indeed, we can find potentials, very explicit potentials, for which the let's say G1, 1 could be also equal to 0. And so let me look at this case now. So, of course, you know, as I said, it's not generically true. So I have to take, you know, a particular potential, and I will tell you what it is, and maybe sometimes also fix some of the thermodynamic parameters, but then I can make it 0, right? I mean, there's simply no sign restriction on that particular coupling. All right. All right, so there's one thing which happens, namely that Where am I? Okay, here. Okay, so there's one. So now I know that this one is 0, and I assume that this one is 0. So I'm at a special point where this happens to be 0. But you see, then I still have two entries which I have to discuss. I mean, these two relevant terms, right? And again, I mean, on those, there doesn't seem to be any particular sign restriction. Okay. So there's one case which people knew already for a long time. That's the case. That's the case of an even potential. So even just means that when I reflect at the origin, it will stay the same, and pressure P equal to 0. Beta is arbitrary. Okay. Well, so in this case, what you find is that in fact, both of these coefficients are actually 0, right? I mean, so the G1 minus 1 minus 1 is equal to 0, and also the G1 0 0 is equal to 0. Okay, so now I have this matrix where these things are 0. Okay, now so you see that the one mode completely decouples from the rest, and the feedback onto the 0 mode is now given by a different scaling exponent, because if there's no feedback, then it's just a Gaussian peak. Okay, so what I have in this case is that sound is Gaussian. So C is equal to 2. And if I plug this into this formula, which I hopefully left here, then you get that in this case the heat is Levy. I mean, so it's the same picture as what I had before, but it's 3/2. The question is, can there be anything else? Well, if you look at the thing, I said, if I take that even potential, then these coefficients happen to be 0. But the question is, are they necessary? If I make simply this assumption, are they always 0? And the answer is no. I mean, there is no restriction on these coefficients, and I can make either both of them different from 0 or only one of them different from 0, right? So remaining cases, I mean, these are in principle 3, right? I mean, remaining cases. So now you have a funny situation. You see, you have 3 modes. I mean, so let me sort of do this in picture so you can understand this a little bit better. So this is 0, +1, and -1. So you see, I still have this coupling here. I mean, so the one sort of couples back, the 0 couples sort of this way, right? I mean, well, maybe I should draw the other way. I mean, so I mean, the 0 is influenced by these two things. Okay, so this is still there. But now I make one of the other couplings also non-zero. I mean, so now I can have sort of a back and forth coupling between, I can do the one mode is now coupling back, let's say, to the 0 mode, right? I mean, it could be also the other way. So I have not only this term, but I also have this back coupling. Okay. So this I always have, but now I assume that this particular coefficient, I mean, this particular coefficient is this particular coefficient is non-zero, right? I mean, this one which I had before, and now I get sort of this back coupling. Well, now I do this argument here. You see, but now I assume scaling, but in this case, I don't know what it is. I mean, this is what I want to compute. Okay. But then I do the back scaling, and then the only way how I can solve this problem is that the only solution when I do this sort of back and forth coupling is that the C has equal to B C tilde. Well, if that's the case, I mean, then you see that I get an equation for C, and the solution is the golden mean. Okay, so in this case, I will get a Levy with an exponent which is given by the golden mean, and I get it for both of them because they have this recoupling. But once I know that this is golden mean, then because there's this coupling, this one also has to be the golden mean. Okay, and so in fact, all peaks are golden mean, all peaks. Now we have a problem. Why? Yeah. So it's slightly different exponents, so, but otherwise it's the same picture. So let me draw the picture why there's a problem. So now I have I have these three peaks, right? So here I have my sound peak. Now here somewhere I have the Levy peak. So here's minus CT, and here's plus CT. Well, there's a problem because they have a slow tail. I mean, out to infinity. I mean, that cannot possibly be. So the reason why there's a problem is because I didn't, this type of argument with the C and C tilde, I did not tell you sort of, the more general form. You see, I assumed that this one is sort of centered at 0, and I got something back which is centered at 0. But of course, the general case is that I have to sort of move them out with the velocity and have to sort of look at that case, right? I mean, this I didn't discuss here. I mean, so I just sort of dropped it to make it sort of a little bit more transparent. So if you do the computations a little bit more carefully, what you find is that what you should exactly find, namely here, it's a symmetric Levy. It's an even function. It's a symmetric Levy. And out here, it's maximally asymmetric. And if it's maximally asymmetric, then this, and with the white sign, then this tail actually becomes very quickly decaying, and this still has the power law. And what I mean by maximally asymmetric, that's the last thing I want to say, is the following, that now, your scaling function looks like e to the minus k. Well, there's a t here. Okay, so then there's the k to the golden mean. So let me just call this chi, for instance. Okay. But then there's also an imaginary part, which is 1 minus I, the sine of k. And what else do you have here? Then you have the tangent of 1/2 pi chi. Like this. So you see, you pick up a phase factor, and your maximal asymmetric. This is a free parameter, but maximal asymmetric is that this parameter. This is the maximal value in the sense that if I would make this even larger, it would not be even a probability distribution. So this is sort of at the border where it's still sort of a positive function, and so this value is the maximal asymmetric. And then there's a plus and minus. This is sort of the minus, and this is the plus. So it looks like this. Okay, and so the assertion is that there's a third phase in which all three peaks are Levy with golden mean as exponent, which is symmetric in the middle and maximal asymmetric at both ends. Okay, so that's the end of the story, and I thank you very much for your attention. So maybe I should say there are no other phases. Okay, that's the full complete phase diagram, right? Okay, thank you very much for listening.
So thank you, Herbert. So I think we don't have time for questions. Sorry, but we are very late. So just 10-minute breaks. You can ask the question to Herbert that you want. And we start at 12. Okay. So thank you again.